So, unit 5 will start today, and it is basically on radiating charges and antennas. So, electrical charges, electrical charge is heart of any radiation, whether it is a static radiation or electromagnetic radiation, electrical charge is definitely sitting there. So, we all know that any matter, any form of matter that we see or that we use does have some charge particles. It means it has got protons, it has got electrons, and from the basic model of atomic binding, we know that we consider that each atom is connected to its neighboring atom by a massless spring, and all these atoms are in continuous vibratory motion, isn't it? We know that all these atoms are in continuous vibratory motion. So, if suppose I have an atom and somehow few of the atoms got ionized, that is electron got knocked out from those atoms, and now the remaining atom is positively charged. Okay. So, if all these atoms, see, I say that electrical charge will give rise to radiation. And if this radiation, if this electrical charge is accelerated, then the resulting radiation will be EM radiation or oscillatory radiation. So, if the charge is static, we will get some radiation. I have a positive charge, and the electric field flux that are coming out of this charge are called radiation. But if this charge starts to move at velocity v is equal to v naught e to the power I omega t, okay. So, this is an oscillatory motion, and such motion would give rise to electromagnetic radiation depending upon what this frequency is. Okay. So, it means charge, electrical charge is the heart of electromagnetic radiation or EM field theory. If there were no charge, there would have been no radiation. So, I was telling you that every matter has got atoms, and atoms have got protons and electrons, okay, as primary carriers of positive and negative charge. So, if somehow and all these atoms in a given matter are localized at lattice points, all the atoms are sitting at lattice points, only electrons are moving. Atoms do not move within an atom. Okay. If atoms start to move, the atoms, if they start to move, then they will become more or less gaseous in nature. Okay. If we have suppose a solid substance, then all the atoms are fixed or localized at the lattice points, and they are only allowed to do vibratory motion. Okay. And if all the vibratory motions are completely synchronized, if all the vibratory motions, I have a lattice distribution, okay, this is suppose a point, and at every lattice point I have an atom, and all these atoms are in vibratory motion like this. And if somehow if I can synchronize all these atoms, and if these atoms are ionized, so they are charged particles. Okay. If these atoms are ionized, then they are charged particles, and if you are able to synchronize their vibration, that is all of them are vibrating in same phase, at any given instant of time all the atoms are in the same position, okay, then the resulting radiation would be something like a laser or a maser, because large number of charge carriers are oscillating in same phase. So, they will give a extremely coherent output radiation. Okay. So, it means if we could do that, then we would not have required a laser or a maser, we could have created laser or maser in every lab, but that is unfortunately not possible. So, what I want to tell you here is that oscillation of charged particle will give rise to electromagnetic radiations. Okay. And these electromagnetic radiation are generally used in antennas. See, if you want to send some radiation somewhere, then you need to use an antenna, and that antenna is called transmitting antenna. Then I need to send some information, you talk on your mobile phones. So, there should be, if suppose a person A is calling a person B, then the antenna in the mobile phone A is the transmitting antenna, but then the information that has generated or has originated from mobile phone A has to reach mobile phone B, but not anyone else. So, it means that these antennas should also be tuned, okay? And the receiving antenna is called a receiver antenna or a receiver, simply a receiver. So, these transmitter and receiver type antennas were first demonstrated by Hertz. Okay. Back in 18th century, it was first demonstrated by Hertz. So, what Hertz did, he took a wire, and he connected two balls, charge carrying balls. He took a wire and he connected the ends of this wire with two charge carrying balls. So, they are capacity balls, they are called capacity sphere because they can store charge in different amount. Okay. Now, the distance between these two balls could be altered. You could change the distance between these two balls, and if this has got effective plus q and it has got minus q, then this makes a dipole, isn't it? This makes a dipole. So, now what he did, he connected this dipole to a transmitter, or you can say a voltage source, variable voltage source. He connected this to a variable voltage source. Okay. Then he similarly connected another arrangement, and then he saw when he increased the voltage, there were sparks here. अब बहुत ज़्यादा ये दोनों चार्ज कैरिंग बॉल्स हैं, आपने वोल्टेज बढ़ाया, बीच में स्पार्क जनरेट हो जाएगी. Now, the moment this spark was generated here, he could see the spark in the wire that was separated by some distance. So, he could say that the electromagnetic radiation, the information that was generated here in the form of spark reached there, which was at some distance. Okay. And these antennas are called dipole antennas, and they were the first antennas. They were the first antennas, and so dipole antennas are also called Hertzian antennas or Hertz antennas. So, these are dipole antennas. Or called so, we will start with dipole antenna, and this concept of dipole antenna was later used by Marconi. You all know he was the founder of modern telegraphy. He did not start telephony, but he started telegraphy. Okay. He could show that he could send information from United Kingdom to a coastal area in Canada. So, he shared his Nobel Prize with someone else for founding the basis of modern telegraphy. So, that what he used were monopole antennas. This is a dipole antenna. A dipole antenna will have radiation pattern like this. This will be the radiation pattern of a dipole antenna. We will see how they will radiate like this, but what Marconi used were monopole antenna. So, they had something like this. So, what does that mean? It means that the radiation here I have in two directions. This is the radiation pattern. So, these are called radiation lobes. So, this is more or less an omnidirectional antenna, because here radiation is only in the one direction. Okay. So, what Marconi used was omnidirectional antenna, and these antennas are still used in wireless communication. Most of the small range wireless communication use Marconi's antenna or monopole antennas. Okay. So, this was a small introduction about antennas and how the story of antenna began from single charge and then to dipole, two charges, equal and opposite charges separated by a distance. But now we will go and see that how actually an accelerated dipole or an oscillating dipole will give rise to such patterns. So, I have two charge separated by a small distance dl. Here I have plus q and here I have minus q. Then I can calculate the dipole moment of this, and that dipole moment P is equal to q dl, is not it? This is q dl, this is the dipole moment. ठीक है? Now, I say that this dipole is oscillating dipole, this is an oscillating dipole. So, I can say if the dipole is oscillating, then the resulting dipole moment should also be oscillatory. बताइए? If dipole is oscillating, then the resulting dipole moment will also be oscillatory. This is moving, so the P will also change. Okay. So, I can say that P has a form P0 e to the power minus I omega t. Now, this P I can write as integral rho dV into some position vector r. Is it okay if I write it like this? This is charge density into small volume is rho dV is the charge enclosed in small volume V and the position vector. Okay. So, rho dV into r, and if I say, because now here I can clearly see that this P is a time dependent variable, this P is a time dependent variable. So, I simply say that dP by dt is equal to P dot. Okay. Now, if this dipole is oscillating, it means this charge is oscillating. Okay. This charge is oscillating with time, the oscillation of charge, the distance between them is not going to change. So, if I do dP by dt here, what I get? I get d by dt of q dl, okay, or I get dq by dt into dl. What is dq by dt? I, current. So, I get that P dot is equal to I dl. So, it means rate of change of momentum is equal to the current element in this wire. I dl I will call the current element. So, I will write here that from this I conclude that rate of change of dipole moment is the current element in the wire. Okay. Now, you see that there is no magnetic field here, there is no magnetic field, definitely there will be some electric field, and now this electric field is moving, it is a changing electric field. Okay. So, now because I know there will be some magnetic field because of the changing electric field, and I know that the divergence of the magnetic field so produced should be 0. Okay. So, if divergence of a given vector quantity is 0, then I can represent that vector quantity as curl of a vector potential or some vector another vector quantity, is not it. So, I can say that B is equal to del cross A, यही लिखते हैं हम लोग, and A we say is the vector potential. Okay. Now, you see here that these two charges are oscillating, they will give rise to some EM radiation, and the propagating wave solutions will be inhomogeneous. हमने ये देखा था in gauge transformation, we had seen that such radiation will give rise to inhomogeneous wave equation. So, we need to find, in order to solve the propagating wave equation coming from these two charges, I need to know A and phi. Phi is scalar potential and A is vector potential. So, I need to calculate A and phi, and we had defined that A is equal to integral mu 0 upon 4 pi j upon r into dV. And we had defined that E is equal to, E was equal to, in terms of phi n A minus grad phi minus del A by del T. This was phi. So, if A is mu 0 upon 4 pi j by r dV, and I know that P dot is equal to I dl, okay, then simply I can say here, I will draw a diagram. See, if I have a dipole like this, and this is the plus q and minus q charge, and I say that I am interested at some position vector r, this position vector r at some point r, okay. I want to know what is the electric field or what is the magnetic field at some point r from the center of the dipole, okay. And if say that angle, this angle with the dipole is theta, okay, and this is r, and I also define another azimuthal angle phi, okay, then I can connect these two. Now, you see, if this is n, if this is nr, if this is nr, and I say that this is n theta, I say that the component, vertical component along this line is n theta, okay. So, this is just a unit normal vector, nr is the unit normal vector. So, the component of unit normal vector along the positive vertical axis n theta would be equal to what? I can say it is equal to nr cos theta, okay. Now, you come here, now I want to calculate this angle in terms of theta. I need to calculate this angle in terms of theta. So, what would be this? Sorry, 90 minus theta of what? Cos of 90 minus theta? बताइए. If say this is n theta, then what will be this in terms of theta? सही बता रहे हैं. Cos of 90 minus theta, this will be n theta cos of 90 minus theta. So, this will be along this direction, it will be n theta sin theta. This will be nr cos theta, simple. I say that this is nr and this is n theta, okay. So, I can write now here, what is this? What is this? This is I dl, mu 0 upon 4 pi integral I dl gives me the scalar vector potential. So, this is I dl. So, I can simply say this is equal to mu naught upon 4 pi p dot, I dl is p dot, okay, into a vector unit normal vector. because field will not be in the direction of oscillation. I know this. Field is never in the direction of motion, it is perpendicular to the direction of motion. Okay? And resultant, so if I take these vectors, so I need to have a vector n, unit normal vector n, which will give me the direction of the field that is being generated or the direction of potential that is being generated. Okay? So now I can substitute the value here and I get mu 0 upon 4 pi p dot n r cos theta minus, because it is in the opposite direction, minus n theta sin theta. So I can clearly see I am dealing with a problem in polar coordinate system. My coordinates are r, theta and phi. Pi है. Mu 0 by 4 pi, this we get from, बताइए, सॉरी, ओके, यहाँ पे हाँ ये पाई है, ठीक है. So now we are dealing with a problem in spherical polar coordinates. So it means this A will have 3 components. This A will have 3 components, A r, A theta and A phi. इसके 3 components होंगे. And these 3 components, A r, A theta, A phi, will be equal to A r will be equal to mu 0 upon 4 pi p dot n r cos theta, and A theta will be equal to mu 0 upon 4 pi p dot n theta sin theta, and there is no phi, so A phi will be equal to 0. A phi will be equal to 0. So it means, now you see this, if you have to understand what is theta and phi. So if I have a current carrying wire like this, okay, if I move around this wire, this is theta. Okay, if I move like this, vertically like this, then this is if I move like this is phi. If I move like this in this direction, like this is theta, okay, and then there is a radial direction. So it means I say that A phi is equal to 0. I am telling A phi is equal to 0. So it means there is no radiation in the equatorial plane. There is no radiation along this plane. There will be a circle, एक वायर जा रहा है, उसके चारों तरफ आप एक सर्कल बना दीजिए लूप, तो उस प्लेन में कोई रेडिएशन नहीं होगा. So radiations are only in this direction. यदि आप इन दोनों को प्लॉट करेंगे, you will get a radiation pattern like this. There is no radiation in the equatorial plane. Okay, A phi 0 means there is no radiation in the equatorial plane. So I have now found A r, A theta, A phi. It means I have completely defined A, but now I need to define phi, because when I know both of them, then only I can solve or I can find my inhomogeneous wave equation. To find phi, I know there is an equation which inhomogeneous wave equation, and that says that del dot A plus mu naught epsilon naught del phi by del t is equal to 0. ये लॉरेंस गेज है. लॉरेंस गेज में हमने ये एज्यूम किया था, गेज ट्रांसफॉर्मेशन में हमने ये एज्यूम किया था, बिकॉज phi and A are defined by us. So if we assume that del dot A plus mu naught epsilon naught del phi by del t is 0, then it will not make much of a difference. Okay. So what I can write from here, this is Lorentz gauge, यहाँ पे चाहे आप लिख लीजिए. So from here I can write from this equation that del phi by del t is equal to minus, this will be 1 by c square, this will be 1 by c square. So it will be c square del dot A. So, it means if I can find del phi by del t, I know A, I can find divergence of A, and then if I differentiate the whole equation, whatever I get, whatever expression term by term with respect to t, I will get del phi by del t. Or what I can do, if the resulting expression, if I integrate it with this, rather we will have to integrate it with respect to t, and I will get phi. Okay. So, now the first question is, because now my A is in spherical polar coordinates, so what would be divergence of A in spherical polar coordinates? So, if we go back to our first few lectures, you will see that we had written like this: the coordinates are r, theta and phi, and the multipliers were 1 r and r sin theta. यही थे देखिए. So, we got del dot A as 1 upon, if I call them, if they are f, g, h, यही हमने माना था पहले. So, I can write that del dot A is equal to 1 upon f, g, h into del over del r, g, h, a, r plus del over del theta, f, h, a theta plus, I do not need to write this because a phi is 0. You can check this. So, now we have to simply substitute the value of f, g, h. So, what I get here is 1 by r square sin theta, and here I get g h. G h is again r square sin theta into a r, and f h is r sin theta into a theta. Okay. So, now what you need to do is, you need to calculate del dot A into c squared. So, when we do this del dot A, so I calculate this. So, I can say that phi is equal to integral c square del dot A dt. ठीक है. Phi is minus c square del dot A dt, and when you solve this, you can do this, you can substitute the values, and when you do this, you get mu 0 p dot upon 4 pi epsilon naught p dot cos theta by r square plus p double dot cos theta by r c. So, this you try to do it. I will tell you here, when we do gauge transformation, we use retarded potentials. If you remember, we want to calculate something at some earlier time. Okay. So, here we will have this, I can tell you here that del dot del t of p dot t minus r c, which is some retarded time t dash, and this is equal to minus p double dot by c. This you can check. So, using this result, you can arrive at this expression. Okay. So, please do it, try to do it yourself, because it is not that difficult. You have to just simply substitute the values and you will get a very simple expression and then you integrate it, you will get this result. So, by calculating A and phi, now for this particular oscillating system, we can find the wave equation, inhomogeneous wave equation, and we know we have in the last unit we had derived the solution of these inhomogeneous wave equation. So, those solutions of E and B will give us the radiation pattern, which I had already drawn actually. The radiation pattern will be more or less similar. So, we will get the radiation pattern of a dipole oscillating antenna, and dipole oscillating antenna is important because first thing it is the fundamental one, and second thing it can be analyzed easily. Okay. So, this is all about dipole antenna. We will do little bit more in dipole antenna. There are different terms in dipole antenna. So, there are different parameters which are to be defined. I think there is no derivation for that, but we will do it.